Same way.
Yeah, that was
There's at least some that are.
Good storage.
Okay, let's look at these. This next second problem set, right? So there's a quiz on this. I don't know if there's a. I think there's. I don't know if there's a quiz every problem set, but there's a quiz on this one. So I'll be sending it out sometime today. It'll be due next week, Tuesday, I think. Okay. And you can view your graded quizzes. Some of you already have, and they're in my office. But they got to stay in my office, right? I want to use these in the future. Okay, so we're actually covering two chapters here. The first one is on vectors, chapter 3. So there's a question. This is number 9. So we're given this relationship. And this is actually very practical. It's the magnetic force on a charged particle, a charge q moving with a velocity v in a magnetic field. Do you guys take 1322? That's the next introductory. Yeah, that's electricity and magnetism, so you'll get this. And this problem is kind of interesting because usually we know these vectors and we find that. But here, this is what's called, the technical name is an inverse problem. And there's a lot of famous inverse problems. Here, we're given f and v, and we need to find b. So you have to think a little bit. It's not just kind of plod along and just do it. So we're going to assume positive charge, q is positive, and we're going to assume, this makes it easier, and I think I'll comment on this, that b, which is what we're trying to find, is perpendicular to v. So in the first case, we have a velocity this way. Typically that's x, this is x, y, and z, but it doesn't really matter. These are orthogonal directions here, right? This is a perspective drawing or whatever you call it. So we're given the velocity here, the force is here, and the question is where's the magnetic field? And it has to be such that v cross b is in the f direction. And there's only two possibilities here if b is going to be perpendicular to v. It's either this way or that way. So you can just pick one and try it, and you can see that this is what works. If you take v cross b, you get f. If b were pointing this way, you'd be getting the force in the opposite direction. So here's a couple of other ones. In this case, now v has been moved to this direction. Again, there's only two possibilities for b here. And this is the one that does it.
So is there some sort of algebraic way you find that? Because I didn't understand this at all.
You didn't know? There can be. I would recommend not using it. You can do it all algebraically. And I can see it wouldn't be that difficult. But what normally everyone does here is they just look at this and just,
so
you know.
V is in the z direction, is coming toward me? In the first example,
no, okay.
working out of the paper.
I think you're having trouble seeing this in 3 dimensions. This, we can't, this is 2-dimensional here, right? So this axis right here is really coming straight out at you. Is that what you just said? Yeah,
yes.
That's right. So, and you can look at it that way. You can imagine this. Well, most people, well, you can do it this way, or you can imagine that V's coming out like that, and then we see, and B's got to point one way or the other, right? We're given that.
Right, because it's perpendicular.
So now you see that V cross B is F. This is the one. So here people would usually write this V out. But you're right, you can do it analytically. It wouldn't be, and in this case, it wouldn't be too bad to do that. Yeah?
I mean, I'd agree with him. For the sake of not guessing, is there just something that I can write? Because I'm doing this stuff right.
Why don't you guys work on that and drop by my office?
Okay.
All right? Yeah. Just represent them analytically with unit vectors And if you're interested, if you can always drop by my office. Okay. Now, one point here. Suppose we weren't given this. So. Then, if you want to think about that, the answer, maybe you can see it, is B can point anywhere in the xy plane here. This is the xy plane. It can actually point anywhere in this half of the plane, because you can see that V cross B is always going to give you a force that way. So it could point anywhere like this, not in the other direction though. If B points back in here like that, it's going to flip the direction of F. Oh, I didn't know this one would be so challenging. Okay, any questions about that? Oh, and I'm going to change this for the future. We can do minus charge. What if the charge is minus? What's going to be the answer to this? What if you're going to have to flip it, right? Because, and here's the procedure you go through. V cross B is this way, but because there's a minus Q, the force is going to be this way. So the answer to the question for a minus charge, you're going to have to choose the B to be this way. That'll give you the right direction. So most people just ignore this when you'll do this next quarter, I guess next quarter, or whenever you take the 1322. They do this, and then when it's a negative charge, they recognize they have to flip the sign for the force. Okay, the next one is a problem. It's problem 17. So here we're given two vectors, and we're given the magnitudes and the directions of the vectors. All right? And we're going to find, basically what we're after here is the sum. We're after the vector sum, and we're going to do it with components. Okay? So, and once we get the sum, we're actually going to go to the magnitude and direction. So it's kind of like we're making almost like we're making a big circle here. We're given the magnitude and directions here. We want to find the magnitude and the direction of the sum. And you might think there's a direct way of going to it. There is, but it would be complicated. So we're going to express these vectors in components, add the two vectors, and then find the magnitude and directions once we know the components. So here's A. What's the x component? Well, you can see from the trigonometry here, we have this right triangle. The x component is this, so it's going to be 10 meters times the cosine of 30 degrees. That's the x component of A. So I can write A like this. Here is its x component with the unit vector in the x direction. And similarly, the y component is going to be same thing except the sine of 30 degrees rather than the cosine. So I can analytically represent the vector A like this. And I punched in the cosine of 30. This is simple. This is actually, the sine of 30 is actually 1/2. This is 1 over the square root of 2, I think. So anyway, we get this analytical representation of A. We do the same thing for B. Oh, now you have to be careful. B, this is going to be the x component. This is going to be the y component, right? So again, we can use the trigonometry. It's the magnitude of the vector times the cosine of what angle do we use here. And if you have a hard copy, you may want to write this down. I did on mine. This is the relevant angle. It's the angle from the positive, counterclockwise from the positive x-axis. So the angle we use is 135 degrees. So you can write an arc here and write, if you've got a hard copy, and write 135 degrees. So we just punch this in, and we get this. And as a check, you know this has a negative x component. And sure enough, it's negative, and positive y. And these are incidentally, these are both positive for A. So the sum is now very easy to do. The x component of the sum is just the sum of the x components. And the y component is the sum of the y components. So I'm just going to add these two things together. Adding the x components give me this. Adding the y components gives me this. And now we have our sum represented as components in terms of unit vectors here. Now to find the magnitude, we just use Pythagoras. It's going to be this, the x component squared plus the y component squared, and then take the square root. That's what I did here, so that's the magnitude. And the direction, we find the angle whose tangent is the y component divided by the z component. And you always want to check to make sure this is reasonable. Remember, you could be in the wrong quadrant. But in this case, there's no problem. This is reasonable. This being 82.5 degrees is very reasonable.
Did you say the z component?
No, I didn't. If I said that, that was wrong.
Okay.
Yeah, this is a purely a two-dimensional problem.
Okay.
So maybe I was wrong. Okay, any questions about that one? Okay, the next one is 33. So now we're given two vectors. This is again a purely two-dimensional, looks like a purely two-dimensional problem. So in the xy plane, we're given the magnitudes and directions. And now we want to find the dot product and the cross product. So here's one vector, r. We're given its magnitude, and it's 40 degrees this way, clockwise. Okay, the minus means clockwise. By convention, remember, counterclockwise is the positive direction from the x-axis. That's a standard convention. So, the dot product, there are different ways of doing this. This is the shorter way, I think. The dot product is the product of the two magnitudes times the cosine of the angle between the vectors. Okay? What's the angle between the vectors? Well, you can see I've drawn it here, right? It's going to be 85 plus 40. This total angle here is 125 degrees. Now there's another possibility. This can also be considered the angle between the two vectors. 360 degrees minus 125, whatever that is, that's this angle. It doesn't make any difference in the dot product, but you've got to be careful in the cross product. I have a little footnote here. If you don't take the smaller of the two angles, what's called the acute angle, you'll be off by a sign here. So you want to be careful about that. So that's why people always go to the smaller of the two angles, which, as I said, is you can see from the geometry here, is going to be 100, and the sum of these two, taking the absolute value here, it's 125 degrees. So the dot product, we're given the magnitude, so I multiply the magnitudes, cosine of 125 degrees, and it's minus 18. Oh, it's negative. Is that reasonable here? Is that a reasonable result? Yeah, and the reason is, it lies on the other side here. So, because the one way of looking at it is, once your angle becomes more than 90 degrees, which this is, the cosine of that's going to be negative. It's going to be negative. Another way of looking at it is, you can think of the dot product. There's another problem where we'll get into this. You can think of the dot product of this vector along this direction here. The dot product involves the product of this magnitudes times the component of this vector along this direction. And the component of this along this direction is opposite that. That's another way of looking at why it's negative. And we'll actually look at that. There's another problem here that we'll look at that. Direction. Where's the direction of the cross product? Straight out, right? Which is the positive z direction. So that's in there. We'll get that by the right-hand rule. Remember, the cross product is a vector. The dot product is a scalar. Okay, this one's going to upset some of you. Okay, but that's okay. Well, so because you see this We had some trouble with this before, right? But that's okay. So we can get around that. So we're given two vectors. Again, it's all in a plane. The two vectors that we're given lie in the same plane, the xy plane. And we want to find a variety of things here, the cross product, the dot product, and then the sum dotted with b. And then finally a d, a component along a direction. We'll talk about that. So, what's the cross product? Well, you can look up the formula. We have a formula for it in terms of the x and y and z, but in this case there are no z components. You can just plug it into that formula. Remember, it's long. In fact, it's so long that the way a lot of people remember it is they take this determinant. But if you're uncomfortable with this, just use the formula. Is that clear? Okay, you should get the same answer. If you don't, then there's a mistake somewhere. So the standard way of doing this is we take this determinant, and this determinant, one way of doing it is you take this times the determinant here. Well, the determinant here is this times this minus that times that, it's 0. The determinant, the subdeterminant for this direction is this times this minus that times that, that's 0. We only get a non-zero value in the k direction, and it's going to be this subdeterminant here, which is 3 times 4 minus 2 times 5. 2 times 5. It's the product of this minus the product of that. It's always, that's the way it works with determinants. So you see, I think I wrote it out here. So you can see here's the 3 times 4 minus the 2 times 5. So we get 2 in the k direction. So, this is nice. For you guys, this is not a big deal in this class. You don't really need to worry about it. Just use the formula. If you don't like the determinants. If you feel uncomfortable with this, just use the formula. So what's the dot product? Well, you remember the dot product is, of course, the product of the components. It's implicit there, but we add the products of the components. And in 2 dimensions, we'll just have this. We'll have another term that was 3 dimensions. So that's what I've done here. And I get a number. And it's 26. Okay, and dimensions aren't important here. Okay, now this gets a little bit more interesting here. Suppose you want to determine this quantity. Well, what I did in the past was I just did this out and then moved on to the next part, and that was wrong. It's always good to stop and think a little bit. So let's look at this though from this point of view. I'm going to do the sum, okay, which the sum is just going to be, I add the components, it's going to be 5 in the I direction and 9 in the j direction. So that's the sum. I want to dot with b. I've substituted in what b is. And now when you take the dot product here, I dot this times this and I get 10, right? What's this? What's this dotted with that? 0, because they're perpendicular. And similarly, that's 0. So taking the dot product here, I'm just multiplying the x components, 5 times 2, and adding it to the product of the y components, 9 times 4, which is 36. There's another way to do this problem, though, that's actually easier. Do we have to plug in what we know these vectors are here? What can we do with this? How can we, what's another way of doing this? Yes, exactly. So, let me write this out. B, okay. I can go ahead and don't plug this stuff in, just go ahead and distribute the dot product here over these 2 terms. And I'm going to get A dot B. And what's B dot B? Yeah, it's B squared, and we take the arrow off. It's just the magnitude, where B is the magnitude. And now, this is probably how they expect you to do it. I just didn't see it before. We already did A dot B, right? Okay, and what's the square of the magnitude of B? Well, that's not too difficult. It's 2 squared plus 4 squared. It's 4 plus 16. That's it. Yeah. Is that right? 4 plus 16, which is 20. So look at that. Same answer. Right. So that's actually easier. So I wrote that in, and next time I teach this course, I'll rescan this. And someday I may type these, but I don't know. It takes so long to type all this stuff up. Okay, oh, we're not done? Sorry. So, part D is the component of A along the direction of B. Okay? So this is in general. In fact, there's in the notes, in the typed notes, there's a diagram that looks like this. In general, vector A and vector B here, the definition of the dot product, AB cosine theta, can be interpreted as this times the magnitude of B, where this is the component of A along the direction of B. That's what this is right here. I project A on B and I get this. I get A times the cosine of theta. So when they ask for, that's the first thing to recognize here. The component of A along the direction of B. Okay, so what we're after is A cosine theta, but that's just equal to A dot B, but not quite, is it? We've got to B. How do we get rid of that B, the magnitude? Well, we need to take the dot product and divide by B. In other words, we need to dot A with a unit vector in the B direction. When you take any vector and divide it by its magnitude, that vector has unit, the magnitude is 1 of that vector. So we can put a hat across on top of it like that. So this is what we need to calculate. This is going to be what we're after. We're after A cosine theta, the component of A along the direction of B, and it's going to be the dot product divided by B. So this is nice. This is an analytical way of finding this. You could do it, you know, all this can be done geometrically, but this is a lot cleaner. So we just do what this says. We take the dot product, which we already know. The magnitude of B is the square root of the sum of the squares of the components, and we get an answer. Okay, any questions about that one? So now I move to the next chapter. So this is kinematics in higher dimensions. And there's a conceptual problem, a couple of conceptual problems. So these are called questions, right? So 7. So if you look at, so there's a diagram in the book here of three different projectiles, 3 different projectile motions. And they start at the ground and they end at the ground, same elevation for the starting and end points. And they all reach the same height. So one of them looks like this, okay. Another one looks like this, and another one, whoa. Looks something like this. Okay, this is conceptual stuff. It's qualitative. Okay. So, rank the times of flight. So this one obviously has a longer time of flight, right? It takes longer to do this than to do that. Is that right? No, it's not right. In fact, maybe let's see. What's the order? What order do they ask this? Yeah, the order's screwed up. We've seen that before. First thing to actually ask to look at here is to think about the x and y components of the velocity. So we have some of the initial velocity. The initial velocity is going to have an x, for each of these is going to have an x and a y component. What's the relationship between the y components? Yeah. You know, if we just care about the y motion, we can forget the x motion. We can just look at this. This is a universal symbol for an eye. I don't know if it is. Like an eyeball? Okay. So if we look at this, from here, what do we see? They all go up together, they all come down together, they all have to have the same y components. So that's one of the critical things here. That's what, and I did it here. That's the first thing to notice in this problem. They all have the same y components. Do they all have the same x components? No. This one is going to be greater. It's covering more ground, and you can see it here. So our situation is this. We have v0 in the x direction, v0 in the y direction. This is the same for all of them, but this is going to be the smallest for this one and the greatest for that one. So we just ranked those. They might ask that, but it's just natural to recognize that. The next thing is, what about that I would look at, what about the time of flight? How do the time of flights compare? Well, again, see the eyeball? What do you see?
Same.
They all have the same time of flight. Exactly. Right. Yeah. Go ahead.
Just so I can make sure, you need to switch your x and y, correct?
Yeah, I don't know how that happened. So my excuse, you can always come up with excuses, is I had a breakthrough in some of my research Friday afternoon. I spent the whole weekend doing a calculation.
You can shift planes?
And pardon me?
We can shift planes?
Oh.
That's the research.
It has to do with the Tacoma Narrows Bridge collapse. Did we talk about that before in here? Yeah, do you guys all know about in 1940 what happened? Yeah, everybody seems to know that.
I know.
Okay, well, Google Tacoma Narrows Bridge and you'll see film of this bridge that just had been built, and it's up in the state of Washington or something. And wind wind can excite oscillations, which is interesting. And what it did was it excited this mode of the bridge predominantly. It was ugly, but it was mainly this torsional mode, and it's one of the most studied disasters of all time. But when they were doing all this intensive study, there was something hadn't been discovered at the time, something called a soliton, and I did my dissertation on solitons. So I had a breakthrough in that it looks like a soliton may have played a role in the collapse of the bridge. Ooh.
What is a soliton?
Drop by my office. It's a nonlinear wave that acts like a particle, but that doesn't really tell you much. But yeah. Or you can look on the wall outside my office with a thesis, my last thesis opportunities. It's mentioned in there. So that's my excuse. So did I get it right now? Yeah. Thank you very much. Thank you. Was that?
Yes.
Damon and Luke?
Yeah, my question was, the big assumption here is that they're all going to the same vertical max height, correct?
Yeah, that's absolutely critical here. Yeah, that's what links these things together. It's a clever, it's good. It's a good conceptual problem. Finally, so the x values have to have this ranking. What about the overall magnitudes of the initial velocity? Well, the magnitude of the initial velocity is, of course, without a vector, it's going to be the x component squared plus the y component squared, right? So these are all the same. Excuse me, these are all the same, but these are ordered like this. So the speeds, the initial speeds are going to be ordered in the same way. Okay, any other questions or comments about that one? Okay, so there's another question here. Oh yeah, this is I haven't resolved all of this yet. Maybe you guys can work on this. Okay, so let me try to convince you. So first of all, starts off pretty simple. Is it possible to accelerate while traveling at constant speed? Yeah, and the one standard example that you think of is uniform circular motion. When you're moving in uniform circular motion, that's constant speed motion. Okay, if here, you have a velocity here. At some later time, the velocity is here. These things have the same speed. So we take the vector off. The speed is the same. But there's an acceleration. And there's a change in velocity because the velocity changes direction. Anytime you have a change in velocity, you have an acceleration. It doesn't matter whether you're changing the magnitude or the direction or both. You're going to have a non-zero acceleration because it's the change in velocity. Is it possible to round a curve with zero acceleration? No way. You've got to change your velocity, you're going to have an acceleration. And now the interesting one. Can you round a curve with a constant magnitude of the acceleration? Well, we know that if you do it if it's uniform circular motion, okay, if the rounding that you're doing is, oh, incidentally, we talked about this in lecture, and we assumed that a car was rounding a corner at constant speed, and I said, that's a model, and that seems reasonable. That's not really what happens. I thought about this later. How do you round a corner? Do you have constant acceleration when is it constant speed? Constant, well, let's assume a constant radius. Let's just assume a constant radius. Do you go with constant speed? No, what do? You decelerate coming in, you accelerate out, right? And if you're my wife, that acceleration is much bigger than it should be. The deceleration just slams on the brakes and okay. Oh, that's right, yeah. She'll never watch this. Okay, so the question here, and it's an interesting one, if you look deeply into it, can you have a constant magnitude of the acceleration? Well, we know the answer is yes. If it's a constant radius of curvature, and the speed is constant, then the acceleration is v squared over, it's constant. The magnitude of the acceleration is constant. It's continually changing. Right at this moment, the acceleration's here. At this moment, it's there. Okay? What if the radius of curvature is not constant? They don't really tell us, if you look at the problem from a general point of view. So can you get constant acceleration? Well, you might think, okay, r is variable. We just have to vary v such that v squared over r is a constant. It's not that simple. Why? What happens when you vary the magnitude of your speed here? You're going to pick up another acceleration. Besides the centripetal, you'll pick up a tangential acceleration. If I'm increasing my speed here, there's always this, centripetal acceleration, but there can be a tangential, and so they're asking about the magnitude of the acceleration. Now you have you have this centripetal and the tangential, and I don't know the answer to this. I've never tried to work this out. It may be possible, if you don't have a constant radius of curvature, you might be able to vary the speed such that a is constant, but it's not obvious. It's not obvious. So that's looking probably a little too deep into this. Okay, any questions about that one? Okay, so now we get in, now we get into the problems. This book has evolved over decades, right? And they just keep piling on problems. You notice that? So the problem is if they omit a problem when they go to a new edition, there's going to be some professors that complain, oh, that was my favorite problem, and I'm not going to buy your book anymore. I'm just going to scan the old edition. And sound familiar? We don't want to talk anymore, but no.
This is being recorded.
Okay, so 27 here involves a plane that's launching this radar decoy. Yeah. That was in Dr. Strangelove. One of the greatest movies of all time. Yeah. You guys have seen it all, right? Yeah. Oh, come on. You missed it? Okay, yeah, it's one of the most popular movies of all time. Yeah, they launched some radar decoys, I remember. Okay. So we're given, here's the situation. The plane is at the moment, it's a projectile motion problem. Okay? We don't need to worry about what's happening, what the details are here. We've got a projectile that's being launched. It's just being released, so it's going to have the same initial velocity as the plane. The plane at this point is directed 30 degrees down from the horizon. It releases something from rest. So that's going to be our initial direction of the projectile. And we're neglecting air resistance here, right? Okay, we'll talk, later in the course, we'll talk about air resistance, but only fairly superficially. If you want to know more about that, you've got to go to a higher level course. Or take a course in fluid dynamics at a higher level. I don't know if you guys take any fluid mechanics courses. I don't think you guys do. Oh, the USW? Did you guys take fluid mechanics here?
Yes.
You should. You really should. Undersea warfare. Okay, good. Yeah, in the physics department? Yeah, it's Ph1121. Yeah, okay. Okay, so here's the situation. It's not it's not projected horizontally, it's projected at some angle. What do we know? We're given this range here, the horizontal distance. Okay, it hits here. We're given the initial speed, which we, without thinking about, well, no, I shouldn't say that. We immediately have to convert this to meters per second. So that's what I did here, okay? You can do it in one shot, however you want to do it, just do it correctly. So we got to get rid of that. It's really the first thing we do. Now, we don't know the height. We're asked to find that. We're also asked to find the time of flight. And it's good to do the time of flight first, because we can look in the, things are simple in the x direction. There's no acceleration. So again, imagine, the eyeball is now up here, right? What do you see? I'm going to see these things, they separate from each other. I'm going to see them separate because this has a bigger x component than this. But they're all moving with constant velocity in the x direction, no acceleration. So I know how to handle that. If I know the initial x velocity, I know that's constant, and I know the distance, I can find the time. That's just distance is velocity times time, because velocity is distance divided by time. So I just solve for the distance. So this is very simple because there's no acceleration, and we find 10 seconds. Now, it's actually good to know this for the next part of the problem, because we want to look in the y direction now. How do we find h? Well, we know the initial velocity, we know its magnitude and direction of the initial velocity, and we know the time of flight now, so we can use this simple position versus time. There's the, remember, here's how I encourage you to do it. This is very general. It holds true for any constant, as long as the acceleration is constant, this is going to be true. Now we specialize it to our particular case. What's the final y? Well, I've chosen my origin here, right? You can get the same incidentally, and some of you have already done this, I think. You can choose this to be your origin. You can choose this to be x equals 0 and y is equal to 0. It's going to just change. It'll change things in here, but the answer is going to be the same. The answer can't depend upon the origin of coordinates. Believe me, this projectile doesn't care at all about what we call the origin. It doesn't care. So, I know the initial, in choosing this to be my origin, right here, the initial y is 0. Excuse me. The final y is 0. The initial y is what we're calling h here, which is what we're trying to find. The initial y component is v0, the speed, which we know, times the cosine, times the sine. We're looking in the vertical direction. We need to find this component. So it's the sine. And you got to be careful here. You know, doing stuff analytically with equations is kind of nice in one way because you don't have to really think that much. You just kind of crank away, but you've got to be precise, right? I'm not going to put in the sine of 30, am I? What is it? It's minus 30. That makes a big difference. If we don't put the minus sign here, then the thing's going to be doing this. It's different. Get a different answer. So you got to be careful. You got to do just what it says here. So I'm doing this 1/2 gt squared. I put in the time and I get a number. That's the height. Okay, any questions about that one?
For that one, you put it's negative minus 1/2 gt squared, but you put it plus because the force of gravity is acting positive.
Okay, I was very careful. This is the general equation, right? What we did was we needed to solve for h. So when I brought this over to the other side of the equation, that's how it became change of sign. Yeah, you got to you got to be precise. That's the price you pay for the analytical way. You don't have, in some ways you don't have to think as much, but you got to do exactly what, you got to do legitimate mathematical steps each step of the way. Okay, 39. All right, so this is this is a high speed here problem, and you're trying to hit a target that's at the same elevation as the rifle or gun or whatever it is here. Okay, and this is practical. This is 45 meters away, but it's very high speed. So you have to aim, of course, higher to hit the target, right, due to gravity. But we expect this to be a small angle here. The angle of the initial velocity is going to be, we expect it to be a small angle in this case, right, with such a big speed. So these are like practical numbers here, I think. And we're given the range, okay, and we want to find the height. Where should you aim? So a scope, you can adjust a scope to do this, right? I guess. Okay. So what is h? Well, one of the first things I see when I see this problem is I'm after h, but what I really want to find is this initial angle. That's the more physically important quantity. And that's in our range formula, incidentally. Okay, this is basic. This is less basic. This is something that's tacked onto the problem. I'm going to go for this theta naught. Once I find this theta naught, I've got a right triangle here. I know this distance. I can find h by the tangent function. So I'm going for theta 0. And I want to make a big point about this here. You don't have to solve this from first principles, like writing down the x components and the y components. We did that once and for all, in general, in lecture. This is the range formula. When something's fired from one height, right, or elevation, and lands at the same elevation, this is the range formula. It's absolutely general. The only assumptions are, g's constant, and there's no drag. So, I know r, I know g, I know the speed, initial speed. This is one equation and one unknown, so I can solve for it. So you plug through here, and you get to this point. You need to find the punch in the inverse sine of this number. All this is that number right there. And you can do that, okay? But I want to point out that, see how this is small? We expected a small angle. The sine of any small quantity is approximately equal to that quantity. This is a simple approximation. So I can write it this way. The sine of epsilon, this is when epsilon is small, the sine of epsilon is approximately equal to epsilon. But you need to recognize that this is in radians. So you can actually verify, you can prove this analytically, or you can punch it in on your calculator. And if you feel uncomfortable about this, just punch it in, okay? And I put a note here, just don't worry about it. But a lot of times in physics, particularly at higher levels, it's really useful to make these approximations. I'll be doing exactly this thing with the Tacoma-Narrows bridge thing, because I got an equation of motion that's just a nightmare for this bridge model. So I'm going to be making the small, in that case, a small amplitude approximation. Here it would be, it's represented just, I'll be doing that for sure. Okay, but anyway, you can verify this. You're going to get close. This is going to be close. Now, we can find theta naught in degrees. You guys, have we talked about converting radians to degrees before? 360 degrees is 2 pi radians, or 180 degrees is pi radians. And there's a conversion on your calculator. So here I am just converting. Why is the 2 there?
1/2 sum.
Oh, there's 1/2 there. Oh, this just, yeah, okay. Right, thank you. So I get this. You can go directly, you can go from here, to here. Go from here and you can just punch it in, and don't worry about this if you don't,
If your calculator's in degrees, the 0.61 is what it'll produce.
That's right. It does all it for you. Yeah, there's a little, this can be convenient, but it also can be inconvenient. It's like anything, right? That's right. So is it close? It should be pretty close. I don't know if this, you might see a difference in this figure. I don't think you'll see a difference in this figure. So do you see a difference there?
No.
Okay, I'm sorry. Okay. So this is probably accurate. My suspicion is this would be accurate to 2 figures. So when you do it essentially exactly on the calculator, do you get the first 2 figures being a 6 and a 1? Okay, good. Yeah. We shouldn't be talking about that in this class, but sorry. Now finally, we've got the theta naught. Now we can get, if I know this angle, and like I said, I know this length, I can get this. Because h is just r times the tangent of theta. And you can punch that in, or you can use the very similar approximation. But if you don't want to, you can just punch in whatever angle you got there and find what distance you have to aim above the target. Okay, any questions about that one? So 67 starts off a conical pendulum. This is a conical pendulum, right? Remember we did the demo? Uniform circular motion. And then it's released or cut, or this person releases it, typically the way it's going to be done. At some point, let's say right out here, it's released. So it's going to go in projectile. Its initial velocity right here is like this. So it's going to go in projectile motion. And this is the simplest, non-trivial case of projectile motion, something that's horizontally fired. That's the first problem we did in projectile motion. So it's easy to analyze this. We know that in the x motion, the distance is going to be the initial speed times the time. We can get the time of flight. We've been through this several times now. So once I get the time of flight, I can plug it back. We see here we have 2 unknowns here. We don't know v and we don't know t. But having found the time of flight from the vertical motion, okay, in the usual way, we can now find the speed. And once we find the speed, we can find the acceleration, because it's v squared over r for uniforms. Because this is this acceleration going back to while it was the conical pendulum. It's v squared over r. And that's more than 10 g's. Anybody been subjected to higher g's? Any pilots here?
10.
Yeah, I think 10 is probably painful. I know I'd be throwing up. But so have you been through this?
Yes, I've done. I'm a hair pilot. I did the centrifuge and everything.
Yeah. So how many?
Humans can't really take more than 6 plus.
Yeah. So this, but cockroaches, no problem. We did the experiment when I was in graduate school. We found a cockroach. Yeah, cockroaches, they've been around forever. Yeah, and probably ants, ant. Okay, that was fun. What's next? I don't think it'd be, I doubt it. But the cockroach clearly didn't have any problem. Okay, the final problem here, you have to think of it looks really confusing when every time I look at this problem, I get confused when I look at it. Here's the situation. There's this cheetah moving at a certain speed relative to a truck that's filming the cheetah. Okay, this is a nature thing, okay? So this truck's moving along at 20 kilometers. It sees the cheetah moving 30 kilometers per hour. All right? So what does a stationary observer see? It's going to be the sun, obviously, as we discussed in class. So the stationary observer is going to observe 50 kilometers per hour. So that's the first part of the motion here. The second part, the cheetah abruptly turns around and starts coming towards the truck. Okay? And now, what the information we're given is the speed of the cheetah the velocity of the cheetah relative to the ground. So there's an initial velocity of the cheetah, which we're given in this frame, in the prime frame of reference. We'll call this the prime frame of reference. It's 30, which means 50 to the ground. The final velocity is 45 coming in a negative direction relative to the ground observer. So what is the speed that's going to be observed in the truck frame? If I'm observing this cheetah coming at 45 kilometers per hour toward me, and the truck is moving at 20, what is it going to detect the cheetah speed to be? Bigger by 20. It's 65 kilometers per hour. Okay? Again, it's the common sense transformation. We call it the Galilean transformation. Now the point of this problem is, once you get by this, the point is to find the acceleration in each frame of reference. They each measure their own accelerations, the change in velocity divided by the change in time. And they both get the same accelerations. So why is that? Well, acceleration involves the change in velocity. And the change in velocity is independent of the frame. These two frames are moving with constant velocity. So whatever change in velocity I see in one frame, I'm going to see it in the other frame. So the accelerations are the same in this case. That's the purpose of the problem. Okay, any quick questions about that? Okay, so tomorrow we finally get into dynamics. We start dynamics.